good morning, good afternoon, good day, or good evening. So welcome to this session. This is Jerry Xiang. I'm hosting it. The theme of this session is forecasting methodologies and applications in the high-tech industry. Again, welcome and thank you all for coming to this session. We already got the sixth session this morning, Pacific time, and now is the second sixth session right now. So the first presenter is Samir Manik, a data scientist at Lyft, and there are a few other co-authors. Actually, among the co-author list, I first contacted Sean Taylor. And Sean Taylor actually was the original model creator for a famous forecasting model, Profit. And they hope he can join our sessions today. So without further ado, Shamir, you take over.
Great, thanks, Jerry. Yeah, so pleased to meet all of you and glad to talk about one of the projects that we've been working on. I'm presenting this, of course, on behalf of the entire team. So we work with Sean Taylor on trying to come up with essentially business forecasts that are causally valid across multiple variables. Kind of before I jump into the project itself, I want to give a little bit of context on Lyft for those of you who might not already be familiar with us. Lyft is a two-sided rideshare marketplace focused on connecting drivers and passengers. In order to make the marketplace more efficient, we set a set of policies within the marketplace. For example, things like discounts for riders or additional incentives for drivers. And in general, these policies are determined experimentally. So we have a good causal understanding about the relationship of setting driver incentives to incremental driver hours, for instance. Now, one thing where we deviate from a lot of other forecasting work, including Sean Taylor's profit package, is that we argue that forecasting is only useful in as much as it helps us run the business better. That is, it's only useful in as much as it helps us make better plans and evaluate decisions. Kind of with that, I want to provide a few definitions that I'm going to be using throughout the talk before jumping into, again, the project itself. So the diagram you're seeing on the right has 3 nodes within them. These nodes are variables within the diagram. You can think of them as any sort of data, and they can either be observed or latent. The blue one, the policy variable that you see, that's a kind of special one. That is something that we believe we have control over. For instance, the rider discounts that I was mentioning earlier. The arrows between the nodes are causal relationships. These are assertions that we're making about the, again, causal relationship between nodes, between variables. And kind of analogously, missing arrows are assertions that there is no causal link. That is to say, because there's no arrow between policy and observation B, we are asserting that observation B is independent of the policy given observation A. There, of course, is the relationship, but it's all mediated through observation A. And then overall, this diagram is called a causal directed acyclic graph, or a causal DAG. For a much more complete, much more thorough explanation, see some of the work by Dr. Judea Pearl. He's written extensively about how this can help you both empirically and in modeling. Great. Now going back to our specific project. Now that we have a bit of nomenclature out of the way, we want to be able to understand and use our levers effectively. And levers at Lyft are things like coupons, rider-facing coupons that lead to sessions. Session is a measure of rider demand. And generally, these are learned experimentally, and you can kind of see on the right-hand side, this is an illustrative relationship between coupons on the x-axis and the number of sessions on the y-axis. Of course, because we're a two-sided marketplace, we have more than just one lever that affects everything. We have driver incentives, which affects driver behavior, and pricing, which affects both rider and driver behavior. These are of course, alongside coupons, and you can think of numerous other potential policies. We have things around like ETA estimates or surge pricing prime time. Overall, though, these policies, these levers fit into a model of Lyft's business. On the right here, you can see a overall DAG, again, causal DAG, that we are asserting describes Lyft's business overall. The blue nodes are, again, those policy decisions that we have control over. And we are asserting things like coupons has a causal relationship to sessions, but driver incentives does not. That is to say, we are making a claim that changing drivers incentives will not change sessions. All of these claims, the missing arrows, are actually completely arguable. We made these decisions through a combination of expert knowledge and a lot of experimentation. But because we're a two-sided marketplace, you could argue and disprove any of them, which is why this is kind of informed through experimentation as well as just existing knowledge, ongoing experimentation. As another example, rider conversion, which is another variable, in this case, an observed variable, we are asserting is independent of coupons given sessions. That is to say, there is no direct relationship between coupons and rider conversion in this example. One of the reasons that we chose to structure it as a set of submodels that are composed into an overall causal DAG is that it ends up being roughly aligned to Lyft's science organization. This creates somewhat natural alignment between the submodels, again, those arrows, and the teams we have at Lyft. For example, the driver engagement team is very concerned with the relationship between driver incentives and active drivers, but they may be a little bit less concerned or a little bit less aware of the impact of incremental sessions on rider conversion. That is to say, by isolating specific topics, specific submodels that teams can understand, study, and experiment around well, we're better able to parcel out the work or divide the work across multiple teams. Cool. Now, going into the sort of technical side of the implementation, we chose to implement each node as a tensor, just a high-dimensional matrix. The reason for this is that it allows us to be a little bit more flexible than any alternative. For example, we can express sessions as a tensor that's segmented by time and location. Sessions being a measure of rider demand can be useful when we understand it, when we treat it as a time series. Other variables, for example, some of the driver incentives might need to be segmented a little bit differently by, say, incentive type, time, and location. And then using this structure, we're able to implement submodels. Again, the submodels are just the arrows. For example, we could implement a coupons to session submodel using a multi-layer neural net shown here with some relationship, some correlational relationship to the exogenous variables and a causally supervised relationship to the coupons. This part's a little bit important. We, in order to obey our interface, we require the submodels to be both predictive and causally valid. That is to say, along the causal path. So because we are saying sessions is a function of coupons, that we can measure and add estimates for, we need the coupons to sessions relationship to be causally supervised. However, the exogenous variables to sessions don't have to be causally supervised. For example, we don't control when thunderstorms happen. Therefore, we don't believe it's as important to have any causal supervision between those. And you can kind of extend that using this submodel approach to arbitrarily or somewhat dynamically create different compositions of submodels, different causal DAGs. That is to say, we have that original causal DAG with the 3 policy variables that we showed earlier. But if we're only interested in the coupons to rides relationship, we can actually make a lot of simplifications because of this composable submodel-based approach. And just look at the variables that affect that relationship. On the kind of technical tactical side, we've chosen to implement submodels as PyTorch models to balance flexibility and concision. And that somewhat naturally falls out of the fact that we're expressing each variable as a tensor. We would then, of course, want the submodels to behave well with tensors. Great. Now getting into the impact of this, this overall system, like any good forecasting system, allows us to make forecasts about business as usual. Shown here are time series across a couple of different variables. The text may be a little bit small, but you can see that we're able to make time series forecasts across coupons, drivers, sessions, rides, etc. To be honest, there is no advantage to using our approach for a business as usual forecast, but of course it's supported and is a requirement in our to support the next couple steps. Now, I think earlier on, we said that forecasting is only really useful if we're able to use it to make plans and evaluate decisions. So what we can see here is that we can see the impact of perturbing one of the policy variables. So again, the text might be a little bit small, but if we perturb the coupons variable at some time, we get this orange line. We can increase the level of couponing at a certain time in a certain location. And then we can see the impact both on things that are pretty directly related, like sessions, increases around that time and maybe has some longer term effects as well. And we can also see the effect on things that are not directly causally related. So rides, which is a little bit further downstream, we can see the impact of increasing coupons during that one time period. Some of these can be non-obvious, some of them can certainly be obvious. So that is to say, the submodel on its own could have answered the question of what is the relationship from coupons to sessions, but it might not have been able to answer the relationship of what's the impact of increasing coupons on rides. With something continuous like coupons, we can construct cost curves across these multiple dimensions, multiple variable outputs. So you can see on the x-axis, we have the different coupon levels, and on the y-axis, we have kind of the response across different variables. So in this case, we could not just see the impact of coupons on sessions, we could also see the outcome on downstream variables like rides. And then just emphasizing why we chose to express each node as a tensor, why we chose to include time as one of the dimensions in each node. And so that we can answer questions about the variable relationships over time. In this instance, we can look at the coupon level in period t, which is on the x-axis, against all of the outcomes in period t plus 0, t plus 1, t plus 2, t plus 3, and so on. Of course, this is all only as reliable as the submodel. We rely on the submodel, in this case, the coupon to session submodel, to convolve over the time dimension. That is, capture the kind of time delayed effects that coupons could have. Great. So this, you might have already guessed, somewhat naturally extends to being able to define an objective function. Since we have multiple decisions that we're making, we can define an objective function as a function of both the decisions and the state. If you recall, this DAG is what we described as the DAG of Lyft's business, and we can add an objective function to that, which may be a deterministic function, again, of the state and decisions. And then somewhat naturally, with an objective function defined, we can start optimizing to make the optimal decisions for any given set of levers or set of times. Here is just showing two of the levers that we're deciding over. So driver incentives and coupons, and we can optimize over that. That is, we can maximize f of x and s over x subject to a set of constraints. In reality, this is also very practical, especially if we can make some simplifying assumptions about like convexity and differentiability. Great, and originally, you'll remember that I had mentioned that we want to be able to make decisions and evaluate decisions using our forecasting approach. And creating a DAG composed of submodels with some observable intermediate variables allows us complete transparency into that decision-making process. Shown on the right-hand side, you can see a couple of different time series, the blue business as usual, and then kind of an orange arbitrary plan that we might be trying to evaluate. And we can see the impact of that plan across a couple of different levers on the intermediate variables. So the two levers on top, intermediate variables in the middle, and then an objective metric at the bottom. That is to say, we can use this to build trust, and business owners or stakeholders can also use this to understand what the model is doing, which is kind of an advantage of using this approach over any other approach, really. One other advantage of our implementation, heavily relying on PyTorch modules, is that we're also able to kind of trivially estimate the sensitivity of the objective to each decision. That is, we can figure out the gradient of F with respect to any of the decisions. And an example of that is shown here. We can look at the partial derivative of the objective with respect to coupons or with respect to driver incentives. And we can actually answer how much better decision could we have made. Additionally, separating the model from the optimization also just kind of simplifies the retrospective evaluation of decisions. We're able to use consistent prospective and retrospective models. Of course, a lot of this project is built on work that other people have done. We kind of highlighted a couple of key areas right here. On the forecasting side, we draw pretty heavily and a lot of parallels to multitask learning and deeply supervised neural networks just on the implementation side. On the technical implementation, we rely heavily on PyTorch, as I mentioned. We also extended PyTorch tensors to follow an X-array-like interface that makes it a lot easier to use and keep track. And then on the causal modeling, of course, I mentioned Dr. Pearl's work. We also drew quite a bit from Dr. Rubin's work on potential outcomes, just to help us implement some of the causal modeling. Just kind of very briefly in conclusion, we wanted to use forecasting to make better decisions. And we think we found a pretty good way to do so by composing a set of causally valid submodels. And in general, we would kind of advocate for using this or a similar approach, especially when you use forecasting in a similar way to make better decisions. I appreciate the time. I think we're pretty short, but Jerry, if we have time for any questions, not sure.
Jerry, you're on mute.
Okay.
Oh, sorry.
Okay. Yeah, we have two questions. We can read from the chat board. The first question is from Nasaga. Are all the exogenous variables defined on the DAG?
Yeah, that's a great question. They are not defined on the DAG. So a lot of the exogenous variables, just for simplicity, we're not showing here, but you can think of things like weather or macroeconomic factors that we don't have control over. We're not causally supervised, but are very important for informing the rest of these.
Yeah, the second question from Albert. Could you explain more about causal supervision entails? What does the causal supervision entails? And how your policy variables is treated differently from exogenous variables?
Yeah, so that's a great question. So the causal supervision that I kind of briefly mentioned here, going from the coupons to session submodel, that is essentially that the relationship between coupons and sessions must be consistent with our experiments or with our understanding of the causal relationship. So kind of in practice, you can think of with a neural network like this, you might have some loss function that could be based on observations. So we would want it to be predictably accurate, and that's what we can observe. But then on top of that, we're adding additional loss functions that are dependent on the relationship between coupons and sessions. For instance, we might be having some loss function that is based on the partial derivative between sessions and coupons that can be measured, or in some cases, an entire curve. We might want it to be able to fit every point along that curve as we change the value of the coupons in the marketplace experimentally.
Yeah, okay, that's great.
and then-
Thanks a lot, Samir. Yeah, so because of the time constraint, and then we can exchange views offline. So next, let's welcome a team from LinkedIn. The presenter in this case will be Reza Hosseini. And Reza is a staff data scientist in LinkedIn. And our team got quite a few members: Reza, Albert, Kaishu, Shayam, and Parvez. So Reza, take over.
Thanks, Jerry. Yeah, thanks for the invitation. I'm very happy to present our work. So this is joint work, like Jerry said, with Albert, Shayan, Kaishu, Saad, and Rachid, and Parvez. So basically, I'm going to present our work from LinkedIn, trying to build a forecasting method that works well in production systems. So what I'm going to cover is why is forecasting important for tech companies and like LinkedIn? Why is forecasting challenging? We have an open source library now called GreyKite Python library that this presentation is basically covering what's inside that library, and you can use later, try it if you're interested. In this library, the main algorithm is called Silverkite, but the library has some other functionalities. That's why the name is different. And then I'm going to give you some references about how you can try it out. Okay, so why forecast is important? Probably, people who are in this session, they're probably quite familiar with that, but it's important because we want to do things like capacity planning, how many servers we're going to need, that type of question, next month, next quarter. Also, it's useful for performance management in the sense that a lot of business lines try to figure out if the metrics are on track, are we hitting targets, what is the impact of COVID? These are the examples. And also resource planning. It's basically, it can inform business strategy and how we can sort of, identify opportunities and so on. So now I'm going to talk about why manual forecast can be difficult and can be problematic, for a company at a large scale. Basically, in a nutshell, manual forecasts are kind of ad hoc, rule-based. They are very time-consuming. Sometimes they don't come with prediction intervals, or at least not very scientific prediction intervals. So, at scale, it's very difficult to use manual forecasts. And if you have a platform or if you have a method that works across the company, then we can bring productivity gain, we can bring insights, because we can do this at scale. So we can, forecast a lot of things. We can bring trust because this process is reproducible, and we can leverage because, we can use our best practices across business lines. And that's kind of been our experience in this work. Now, when we want to build automated forecast or automated machine learning forecast, basically there is that works for the whole company, or at least, for most of the use cases, there is a lot of specifications that we have. Basically, we have diverse data. You have a couple of examples, public data in the bottom. The imports, US imports from Japan is one of the plots on the left side, and the COVID weekly death per 100,000 in the US is on the right. So just to show that time series data, they can have very different patterns. We have diverse requirements. For example, the objective can be different. For capacity planning, maybe you care about the peaks more. The ecosystem changes pretty rapidly. For example, due to COVID, large initiatives. Often you need business knowledge that somehow you want to use in your forecast. And explainability is important. Interpretability is important because a lot of end users want to know, have some sort of understanding of how the forecast is created. Some technical challenge, for example, there could be floating holidays and so on. And computational speed is important sometimes. In some cases, when you're running forecasts a lot, on many different problems or live in the context of, for example, anomaly detection. So now I'm going to get into the Silver Sky algorithm design that's sort of motivated to solve these problems and be flexible. And I'm just going to go straight to a diagram to show how the model looks like. So basically, you can focus on the blue nodes, which are the computational nodes, and the input nodes are green. For example, the very left input is just the input time series. And in the first computational node, basically, we are calculating raw features. So we have a timestamp, we can extract many features, right? Time of day, time of week, is it a holiday, is it not a holiday? So, many features you can extract from that timestamp. And in the next phase, basically, we want to go from these raw features and to some basis functions that are going to be, in some sense, more ready to be used in various models. So not only one model, we allow for various models in the next step. So, you can use Fourier series. You need to map, basically what you want to do, you want to map your raw features to some features that could be probably more ready and more meaningful. For example, Fourier series are periodic and so on. So before going to the last step, we also, because ecosystem are very, they change over time, growth changes, seasonality changes. We have a automatic change point detection that figures out some change points that then can be added to those features that are created. And in the very last step, basically, we want to use a machine learning algorithm, for example, a regularization based, it could be ridge and so on. So by design, we allow for multiple, basically any machine learning algorithm here, but ridge is, for example, our default. So regularization based is our default. And so already we have forecast. So in the orange, we have forecast visualization, model components, model summaries, as evaluations, but also we have a volatility model. So in the bottom, we have statistical volatility model. They are kind of simple, but we fit the volatility model to the residuals. And this is by design. The reason that we have separated that, one of the reasons is the computational speed, but also flexibility. So we can swap different parts of this model in terms of engineering and track everything better. And from the volatility, of course, we get prediction intervals, anomaly detection. I'm going to run through some math quickly, relatively. Just I want you to be familiar with how the math sort of looks like through an example with some data. I won't get into too much detail, of course, because of time, but you can look at our, for example, blog posts and papers. I'm going to paper at the end to get more details. So what is a time series? Basically, you can think of a time series as an object where you have, at least two columns, right? You have the timestamps and you have the values. Typically, they are, of course, increasing in time, regularly spaced. I mean, you can extend these methods to other, where they are not regularly spaced, but generally speaking, they are regularly spaced. So you can just think of it as a data frame, basically with two columns, right? And so the very first step was the building raw time features, right? For example, you have a timestamp, you can map it to 0 to 24, that's time of day. You can map it from 0 to 7, that's time of week. Similarly, time of month, time of quarter, and you can kind of imagine why these variables are going to be useful, right? So in business, time of quarter is probably a useful variable. That's why we are creating these variables. Time of year, between 0 and 1, where in the year are we? And a continuous variable, you probably need a continuous variable to model the growth, right? And you still probably need some categorical variables. It might be useful in some context to keep them around, like day of week, is weekend, and so on. The next step is basically creating those basis functions. And you're familiar with Fourier series used in this context. So you can use Fourier series, for example, for different time scales, time of day. You can represent it by what is the feature? The raw feature was time of day. What is its period? That makes sense. It's 24-hour and ordered. And you have to pick the order, right? The Fourier series order and so on. And in this example, you can see here that this is from a bike sharing data from in Washington, DC. And this is sort of the model components. This is the daily pattern. This is the day of week effect. And this is the, the annual pattern. So these are coming out of the model, for example, in this example. And sometimes you want to still use categorical variables if it's too chaotic, or if that pattern is, has very high peaks and so on. Maybe Fourier series, you're going to have need a very large order. So, you may sometimes use, you want to allow for some categorical variables in this context. And this is just this is just the math. I won't get into it, but this is just basically the Fourier series for the time of day. And this is the bike sharing data. This is the, is fitted on some data. And this is the forecast with the forecast bands. They are pretty close. In this example, it's performing well. So we are capturing, those variations during the week and during the day in this example. But, these patterns change quite a bit. For example, Washington, DC, during the cherry blossom season, in orange, the weekly pattern is quite different. So your model needs to account for this, and we account for this. You can easily allow for this and specify this kind of special periods. Basically, the idea is to use some sort of interaction terms to capture these effects easily. Now about long-term growth. So, the continuous time variable, you can take it and you can have linear growth, you can have non-linear growth. But, in this case, you can see that bike sharing demand increased and decreased. So you're going to need some way to account for this. The best, one of the best ways using change points. And that's why we have the change point detection that I'm going to talk about briefly later. Holidays. Basically, you want to allow for holiday to take any shape and form, right? During December, there is holidays, for example, or during Christmas itself. If you look at hourly data, the patterns can be quite different. So you want to allow for deviations during those holidays. So, this TCE is the time temporal coverage of an event, which is basically can happen in different periods. And then you can, allow for the Fourier series to change and deviate during those times in a nutshell, right? So this is sort of has an indicator function, and it allows for the Fourier series to change during that period. This is an example for bike sharing data. You can see that, we've captured those holidays in Thanksgiving, pretty well with the data we had. And with all of that, you're still going to have some temporal correlation left in the time series. Most of you are familiar with that. So that captured a lot of the temporal variation, but to capture the remaining temporal variation, basically to use the recent data to improve prediction, we can use autoregression. For example, what we are doing a little bit different than usual is we are allowing for, because autoregression, you may need a lot of orders to do justice to the temporal correlation, can be, long-tailed in some sense. So it can, you may need too many orders. So we allow for an idea of lag aggregation, which is a very simple idea, but very useful idea. And you can define your lag aggregates to have certain meanings too, right? You can aggregate the whole week prior to time t, and you can do these things. So that would be the weekly average and so on. And we found that very useful in terms of accuracy and model parsimony. And now I get back to the change points. So basically our approach to the change points, if you look at this equation, like if you have a basis function, it can be just linear, right? ft could be just t, but it could be a nonlinear function. Basically, this is a piecewise now version of f, right? So it could be piecewise linear, right? And you can do the same trick for seasonality. You sort of have a piecewise linear in the Fourier series, right? Every coefficient is piecewise linear, right? So like you can see there is a beta here, there's a beta there. And so the same trick you can play with seasonality. And so, but then this form is if you knew that those change points. Of course, we need to discover those change points. And for that, we have an automatic method which uses adaptive lasso, and the equation is here. But basically, we use regularization to figure out where is the best places to put the change points. And maybe I'll just I'll go to the next slide. So these were the components of the mean model, in the sense of like how the time series values are, but volatility is still in play, right? We want to capture volatility, or basically the prediction intervals variance as well. And of course, volatility, or that remaining variance, can be itself, it won't be constant, right? It could depend on time, it could depend on time of week, it could depend on many variables. And basically we allow for that. So in this case, just to show you, how volatility can change with time, this is again bike sharing data. And the red curve is basically the standard deviations that are coming from the observation. So for every time in the week, you can calculate how variable it is. And you can see the standard deviations are changing with time. So we allow for that. In the volatility model, you can specify features to allow for that. This is just a brief overview of how our library works. You can take a look, but basically here is an example of how the model looks like. You can specify forecast horizon and so on. And here in the orange, it shows what you get. So you get exploratory plots, you get model summary, you get cross-validation summary, you get diagnostics, and you get model components, and a lot of good things out of the model. Because the model is fairly sophisticated, we have templates where they're appropriate for different frequency or forecast horizon, and we keep improving them over time. This is just a benchmarking against some great libraries we tried in our case in LinkedIn. And one great thing about GreyKite is very fast as a result of that design, which was deliberate. So for example, it was 10 times faster when we compared with something like Prophet. And in terms of accuracy, when we tried on our internal data and some external data, we got better accuracies in these time horizons, in this hourly, daily, and so on. So we think we are doing pretty well in terms of accuracy, but speed is quite better. And for things like anomaly detection, it's been useful for us. Yeah, that's my last slide. Basically, how you can try GreyKite. You can read our LinkedIn engineering blog post. You can look at our archive paper on archive right now. You can install our library just like any Python library, pip install GreyKite. And we welcome you to come on GitHub and leave us comments. You can contact myself through LinkedIn or using my email. I'll be very happy to sort of hear your use cases or opinions about our work. Thank you very much.
Yeah, thank you, Reza, for a great presentation. Any questions from the audience? So I have one question. So for the confidence interval, you mentioned your algorithm allows kind of time varying. So on a daily basis, so the confidence interval width is the largest on what days?
Good question. So typically the confidence intervals in our experience, so you can specify features. So for example, a nice feature to specify would be day of week. Usually in different days of week, you have a different length in confidence interval if coming out of the model. Typically weekends probably have a higher sort of larger prediction interval, or holidays. So you can specify holiday as a feature, and holidays, there will be more volatility in our experience.
Yeah, I can see. Okay, the width, wide width is caused by more volatility during holidays on the weekends. Yeah.
Right. Yeah.
Any other questions from the audience? If not, okay. Later, if you have questions, you can always contact Reza. Okay. Thank you again, Reza. Okay.
Thank you, Jerry.
So now, okay, let me, next presenter will be me. Okay, let me share my screen. Okay, so can you guys see my screen? Yeah. So, oops, it jumped too fast. So the topic for my presentation today is forecasting with non-parametric models for short term, and then causal effect models for longer term. So a few key bullet points here. First, we wanted to understand the business needs. So as we know, accurate and reliable forecasts for business metrics, okay, we definitely need it always, okay? So this is to create a well-founded and a realistic business plan, right? Okay, once you got this plan, okay, then you need to monitor the execution of the plan, especially the performance of those metrics in progress. So that are the business needs. And then move on. Okay, so the forecasting horizon can be short and long, as I pointed out earlier. Okay, so for instance, when we say short horizon, maybe next day or next week, right? And then the use of for a short-term forecasting basically is for monitoring, alerting, okay, and also the root cause analysis at the operational level. But then when the horizon is long, such as monthly, quarterly, even yearly, the objectives are more on the financial and the resources planning, because those activities usually take a long time. Hiring and firing takes at least 3 to 6 months, right? So, and also RCA at a strategic level is also needed at a kind of a long-term horizon. So in order to build a reliable kind of model for long-term forecast, obviously we need to start from building a reliable short-term forecast model, right? So there's a saying, a journey of 1,000 miles starts from the first step. Okay, we need to have a very good understanding to build a short-term forecast model. So in this talk, we will have a deep dive on the short-term models, and then we'll also touch slightly on the longer-term models. The one cautious note here very quickly. So some people just use the short-term model to serve for long-term objectives. So for that, actually, you have a model risk, because the short-term model usually do not include many long-term drivers, sometimes even no long-term drivers in it at all. So that would kind of provide a overstretch use for the short-term models. Now, let me focus on the short-term models. This window here. Okay, so this is a graph on some kind of transformed real data. On the x-axis, you have Monday through Sunday, and the y-axis is the value of the transformed response variable. Each color corresponds to a calendar week. And in this case, a calendar week is defined from Monday to Sunday. And then you can see, okay, we have a few quick observations. In each week, the daily amounts from Monday through Friday kind of in a narrow range, right? Relatively stable. But then if you go to Saturday, obviously you see a drop from the workday pack. And the Sunday, an additional drop. Okay, so those are the 3 obvious observations. And also the daily patterns, okay, for each curve, okay, exhibits a daily pattern. In a week, would stochastically repeat across weeks, right? More or less. Of course, the relative magnitude can change, but the overall patterns are kind of more or less the same. And then you also from this graph, you can see the first week is black. Okay, that is in February. But then once you get into March, the first week, the red followed by the second week, third week, fourth week. And then you can see the overall level also increased from week 1 to week 4 in a month. Okay, so this is a good observation. Now, yeah. So based on that observation, if we aggregate the daily amounts into a weekly summation, okay, and you can see it here, okay, the x-axis again is for in this case is for the weekly marks, and the y-axis is the total amount for cumulative amount for the week, and the curve in black is the actual. And as I already pointed out, okay, in general, from week 1 through the last week, you have an increasing pattern, right? But then usually, okay, you can see from week 1, 2, 3, 4, okay, so kind of increasing. But then the last week, okay, it kind of reset itself, okay, going down toward for the first week of next month. And then if we want to model this weekly aggregate data, and then you can use a simple linear regression. Okay, of course, that would more or less reflect the overall growing trend. But then the last week, you need to make some adjustment. So from this visual, we can see some suggestions. And we want to examine the data patterns, not only on a weekly visualization basis, but then if you look at it on a yearly horizon. So here, so we have a 53-week in a year time frame. And then for each panel, basically it indicates a panel is defined from a blue horizontal line, dotted horizontal line, and with a solid line. Okay, that defines a month. And a month you got sometimes 4, sometimes 5 weeks. You can see the pattern, okay, kind of from the beginning of the month to the end of the month, always going up, 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 except for December. Okay, December, the last 2 weeks dropped significantly. Basically, toward the end of the year, the data would reset or regress itself to a baseline. Of course, that baseline is a kind of a long-term yearly trend. Okay, but then in a year, you can see this kind of solid patterns. And we wanted to capture those patterns first visually, and then model them. And here are our non-parametric model with a few key steps listed. So we observed day of week patterns, right? Very clear. And then we define a percentage. For instance, okay, DI stands for the amount in day I. I ranges from Monday through Sunday. And then alpha I would define the daily percentage, right, for day I, and it's in a week. And then once you get multiple weeks, and then you can form an estimate, okay? And this estimate we use alpha hat, okay, for individual days. So alpha hat G, for instance, in the second equation here. Of course, in that case, you need to use multiple weeks to come up with the estimate, okay? And then now let me move on to, okay, you can see a few steps here, okay? So we need to create the week to month association relationship. That's important. Why? Because a month doesn't contain exactly 4 weeks or 5 weeks. Sometimes you have a partial week. Sometimes you have partially 4 weeks, partially 5 weeks. So we need to define an exact association relation. In the doc, okay, we will provide a link later, and then you can see this relationship exactly defined. And then, as I pointed out earlier, so we need to identify and model the weekly trend within a month. So kind of going up, but also across months. So in the last week of the month, okay, it will reset itself. So we also need to identify and build a proper model for that. And then you can use the data observed so far. Okay, for instance, in a new week, you have observed Monday's actual, and then you can use this relationship based on this relationship to project for the remaining days in that week. And then if you observed 2 days, day 1, Monday, Tuesday, you can use the next equation. And if you observe the multiple days, you can use the last day equation, okay, to project for the remaining days. And the more actual days you have for a week, the more reliable and accurate you would get from the corresponding models. So now, okay, with the model we just mentioned, okay, so here is the output, and then is a kind of a stacked weekly view. So previously we see a kind of on a weekly basis, different colors, right? And then here, the solid color corresponds to the actual, and the dotted color, the dotted line corresponds to the forecast. And as you can see from this model, the output in the legend, we also have numerical output. The quality is actually very reasonable, okay? So 2.6 and sometimes 0.82, sometimes, okay, and very reasonable. And then this is a stacked weekly view, and then, okay, I need to jump here. Okay, this is a kind of sequential weekly view. So now we put everything in a month for all the weeks. And then now you can see overall kind of a monthly upward trend I mentioned at the beginning, right? So it captured. And then during a week, okay, and the day of week effect, and then also everything captured well. And for this particular case, the map is 2.12 for the whole month. Okay, also very good. So let me move to here. Okay, okay, so I'm jumping too fast. Okay, in this graph, actually, we have provided not only the daily forecast, the daily point forecast, but also we have a detection mechanism behind. So you can see, for instance, in this case, for the last day, the actual is deviated significantly, quite significantly from the projected. Okay, in this case, we detect, we declare a kind of a significant deviation. Okay, and then we use red color in the axis 3 to indicate that. And then sometimes you can see we use yellow color. Okay, that indicates less serious kind of variation. But then if you in blue color, everything is normal. So that would give you a view on the anomaly detection. So this is good for point forecasting. And then we also have a solution for confidence interval forecast. And this would use the resampling method, generate from the kind of regular RID situation to the time series situation. And in the interest of time, so I skip from here. But then the split here is, okay, use the resampling method to the time series setting. Now, let me, so we'll have 6 more minutes. And now let me shed some light on the long-term forecasting models we have developed. So now we are still building models to forecast for a business metric, right? The same as before. But then now the horizon is from T+1 or T+7, meaning okay, 1 day ahead or 7 days ahead, to a longer term, meaning 30 days ahead or 90 days ahead, right? Okay. So in here, as I previously mentioned, we need to identify long-term drivers. That's very important. In the short term, we identify the day of week or serial correlation very strong. But in long term, business drivers are more important than the serial correlation relationship. So we know, okay, there are some existing machine learning algorithms can help us select the features, right? So as Reza mentioned in his talk, so we sometimes a feature can impact your response variable in a kind of lagged way, right? So in that case, you need to consider the feature in a kind of contemporary time fashion, and also a lagged time fashion. And then we list in this solution, we list all the variables together, and then use machine learning algorithms to select important features. The features can be the original feature or a feature with a corresponding lag. And we know, okay, people use lasso a lot, but the lasso is mostly based on L1 or L2 kind of norms, right? for that consideration is basically for mathematical convenience and consideration. But then we also need to get kind of a business judgment into our model building process. So why this particular feature is important and then we cannot ignore, etc. That kind of consideration also need to get into our model. And then you can see here for certain drivers, and we need to call the regular time series method to forecast. And then once you forecasted, you can use the causal effect model we are building. And then very quickly, okay, so this is a random forest algorithm, the output. So you can see from the y-axis, you have the regular drivers with the corresponding lags identified. Okay, this is an example for analyzing certain revenue in certain business segment. Okay, you can see the important drivers listed from the top to the bottom: impressions, clicks, conversion rate, etc. Okay, so this is one method, and the other method is use this, I call it design factor analysis. Sometimes you have a continuous variable, okay, you want to consider. Sometimes you have discrete variables you want to consider. For continuous and discrete, you want to consider them simultaneously. And then in this case, I used a discretizing method to discretize continuous variables so that they can all kind of be compared apple with apple. And the output of here is from left to right. The left meaning the most significant, the right the least important. Of course, the feature's importance is defined by the user, can be the variability in certain form, etc. You can also associate some business consideration there. So once you get this kind of machine learning algorithm-based consideration plus business judgment, and then you can build a kind of a overall causal effective model. So in summary, the day of week effect and the serial correlation effect for short-term forecasting, okay, very important because they are the strongest, and they should be quantified and reflected in the short-term models. The multiple layers of similarity effects, as pointed out here, okay, the day of a week in a week, week in a month, beginning of the week, a month, or end of the month, and the beginning of the year or end of the year. Okay, you have multiple layers, can be significant too, and they should also be quantified and reflected in the model. So those effects are nothing magic. Okay, sometimes we just focus on building models. We thought, okay, those are data driven, but really, so those effects are just a reflection of our users' collective behaviors in the time dimension. That's all. Okay. So once the user behavior changes, those the data also change, and then we also need to change our model properly. The distributional assumptions and the structure assumptions, for instance, Arima hot windows, can bring simplicity, but sometimes you lose the reality because it has a rigorous kind of structure and a significant kind of probability model assumption behind. But then you can see in the non-parametric model we are presenting here, okay, it provides a great alternative model with simplicity and better reality alignment without the distributional and model structural assumptions. For longer term, business drivers and the micro factors are also very significant. And I already pointed out, we need to identify and incorporate them properly. Okay, and then the causal effect model can provide better explainability and the root cause analysis, but not necessary for model accuracy. Okay, because of the data, you got more data, sometimes you got more noise in your model building process. Last but not least, and different business metrics, business segments, even time phases can call for different sets of drivers. So therefore, a kind of model automation capability and scalability is very necessary for the overall success. Yeah. So that is my presentation. Okay. So any questions? Hello? Yeah. If there's no more question, we definitely can exchange our views offline. Again, thank all the presenters and the audience for attending this session.